right, so today we are going to talk about heat pumps. I just pulled up the article on heat pump charging just as a reference. I didn't make like a PowerPoint presentation or anything, but we're just gonna have, for the first little bit, we'll just kind of talk through it, and then we'll actually go through some things on the equipment. Really actively moving my hands.
Is there a place I can find this article to help me follow along?
You sure can. It's on hvacrschool.com or the HVAC School podcast. HVAC School app, sorry. Whew. Okay, that was rough. Here it's going. And you just type in heat pump charging or heat mode charging, I guess you could do that as well. Yeah, so I'm not going to read the entire really long URL. That would be annoying. Actually wrote most of this article, most of what this is, back when I made a little training handbook in my Dell Air days. Just went ahead and said it. And so this is actually a picture of the old Carrier heat pump that I had at my house, Minnehaha Avenue. Isn't everybody excited about that? Yeah, absolutely. Wow. So, yeah, really exciting. So a lot of the rules of thumb still remain. Heat pump, heat mode, heat pump charging and testing, there are a lot of rules of thumb, and they're not like crazy accurate, but generally speaking, our heating season is so short that you're not expected to like, make huge adjustments generally, but you want to make sure that the equipment's running properly. If you work in, if you're out there in YouTube land and you work on equipment where you have really long heating seasons, then generally speaking, you're going to rely more on weighing in, weighing out, that kind of thing. It's very cold, because it is challenging. There are some techniques you can use to be pretty accurate, but they're pretty in-depth, and we'll talk about that. But let's start with just connecting to a heat pump in heat mode. And this is one of my favorite examples of a system that's kind of interesting to hook up to. So we've got our heat mode port, which is always suction, or common suction is what we call it. So that is connected where? Where's that connected in the system, Matt?
Reversing valve?
It's connected, it's not on the reversing valve. It's between the reversing valve and the compressor and the suction line. So if we look inside, and we'll do this in a little bit, if you look inside a unit, the reversing valve, the top and the bottom, so the top's by itself usually, it's the discharge line, smaller line, and then the bottom in the center is the suction line. Those connect directly to the compressor. And then it kind of flip-flops those depending on whether you're running in heat or cool, which basically defines whether or not your indoor coil is an evaporator or a condenser, and whether or not your outdoor coil is an evaporator or a condenser. So whether it's absorbing heat or rejecting heat. Obviously, in cooling mode, we want to absorb heat from the inside and reject it outside. In heating mode, we want to absorb heat from the outside and reject it inside, right? That's the idea. When you're running a heat pump in heat mode, you want to connect your low side to that port. Now, it used to be when you were using analog gauges that it was kind of a big deal if you accidentally hooked your suction gauge to the high side, because it would peg your gauge and ruin it. Nowadays, with digital gauges and probes, they don't really care. Like, it's not going to hurt the probe or the manifold if you connect to the wrong port, because you're not pegging a needle. But obviously, you're going to get an incorrect reading. Go ahead, Bert.
Why does it say retard at the very end of the old manifold gauges? Like, if you had it hooked up on that side, it would just throw your dial into where it says retard.
Yep. That is actually a real question. And it is the source of many inappropriate jokes on Facebook groups, not HVAC School, because we don't make those kind of jokes.
Well,
I'm not at Kalos.
I'm dead freaking serious.
I know, and it is really true. So we'll put it up in the video so you can see a picture of what the old suction gauge looks like, and it does. It has this spot at the end that says retard, and all that means is that when it gets to that level, it actually has like a spring force or some opposing force that keeps it from pegging that needle and breaking it when it overpressurizes. So it goes to a point, and then it actually has something that kind of prevents it from breaking itself. Does that make sense?
So
in that case, retard means like to push against, to inhibit. And that's really what that word means, is it means inhibited or to inhibit.
I just thought maybe it was like the manufacturers telling you were really stupid.
We're not making that joke, we already just said that.
It's not a joke. I just thought that's what they were doing.
Did you actually thought that's what it
I
was?
did. Like,
Oh, you thought that's what it was.
When I
oh,
first
you really
started,
thought that?
Yeah, when I first started, I thought that.
Okay.
I thought they
Yeah,
were
I
like,
doubt
you gotta
I
be
doubt
stupid.
Whereas it used to be a really big deal, it still matters because you're going to get wrong readings if you don't. But you want to connect what was your suction gauge. You know, your suction gauge would generally be hooked to your suction line. And heat pumps, they actually don't call that a suction line technically. Do you know what this line is called technically when your system is a heat pump? What's it called?
The vapor line.
The vapor line. And Jim Bergman was the one who first told me that and made a real big fuss about it. I would just call it the discharge line when it was in heat mode and the suction line when it was in cooling mode, but he insisted it's the vapor line. And that is an accurate name. And why is that an accurate name to call it the vapor line? Eli. Why is it an accurate name on a heat pump to call the large line in between the condenser and the air handler the vapor line?
It always has vapor and it's not always a suction line.
Because it always has vapor and it's not always a suction line, exactly. Because the discharge line is fully vapor, the suction line is fully vapor. Discharge line is high pressure, high temperature vapor. Suction line is low pressure, low temperature vapor, but they're both vapor. Vapor in the compressor, vapor out of the compressor, right? So that's why we would call it the vapor line. And the direction of flow changes. Same thing with the liquid line. The direction of flow changes in the liquid line. But the liquid line always stays the liquid line, right? Now, when I first did this, there was a lot of people who got cranky about this because I said in cool mode, I also said hook here. I probably should have said connect. You know, people can get the wrong idea. But I said in heat mode, hook here and here. Suction here, discharge there. And so people would get upset because they'd say, well, why can't you just leave your high side gauge connected here? Why can't you? Because it's the liquid line either way. So why can I not just leave my high side gauge connected here on this system? You know why, Eric?
On this unit, it's the expansion line.
Exactly. On this unit, it's the expansion line. It says it right here. Expansion line in heat. And the reason being is because the metering device in heat mode is located right here. That's the metering device. And when you get past the metering device, you either call that the expansion line or the evaporator. Right? It becomes the evaporator. And so, whereas right here, this is high pressure. That's not where my port is. Right here is where my port is, and that's no longer high pressure. Now it's also not completely low pressure either. If you ever measure it, you'll notice it's higher than your suction pressure because it hasn't had a chance to fully expand yet. But it's certainly not high side anymore in heat mode.
Isn't that more of a carrier thing though, to have the metering device outside the condenser?
It's very much a carrier thing. It's going away, and so it's maybe kind of an arcane, but you'll still see a lot of them out there like that. If you're working on most brands where the metering device is inside, whether it's a TXV or an Orphis or whatever it is, well then you could leave your high side connected there. In fact, I would recommend that you do, because now you can measure subcooling, right? You can't measure subcooling accurately when you connect to a discharge line, because the pressure in the discharge line and the pressure in the liquid line are different, right? So in heat mode, they're different. Go ahead.
How do we know if that's when the metering device is on the system?
So it just takes some system knowledge. Obviously, you know, if you've ever installed a carrier system, you know that you're putting a piston in here. Whether or not you have the old school, this is an R22 system, this is a flare fitting. This is what they used to use. And so when they came shipped, they would have a cap there, and they'd have a little bag with the piston, and you put it in, or it's behind the cap. Whereas nowadays with R410A, they use a chatlet fitting with a Teflon O-ring. So just experience knowing that.
So let's say, because I'm used to working on Goodmans specifically,
Okay. Yep.
or trains,
Yep.
systems of those. We didn't have a lot of carriers where I was located.
Mm-hmm.
So if I were to walk up to one of these, how would I know that I need to connect at this line
Versus the other.
versus the other line based on the system itself would not?
Easiest. So again, it's I don't know that there is anyone other than Carrier who does it this way.
Okay.
Does anyone else know? I think it's only Carrier. So Goodman will use a heat mode piston sometimes, but it's inside the cabin. Lennox is pretty much going to use always TXVs. Even modern Carrier systems are going to a lot more TXVs in heat mode inside the unit. So that's going to be self-evident at that point. But you're always sort of looking for, the easiest way to think of it is, there's always a metering device somewhere. So identify where it is. And if you look inside this unit and there's no TXV in there, and it's a heat pump, that kind of leaves right here at that point, you know, and that is right where it is. So it's sort of process of elimination. It's actually an interesting thing, and this I'm going to go up on a little side note here because it's a similar topic. You work on a lot of RTUs, kind of small, medium-sized rooftop units. you're going to notice that you trace down your liquid line, and all of a sudden it goes into a header, and then it just goes straight into the evaporator coil. There's like, you don't see a metering device. And I remember seeing that, like, what on earth is going on? But actually there's all these little header crimps, and those header crimps act as the metering device. Because what is a metering device? How would you define a metering device, Joel?
Controls the amount of pressure going through.
Yeah, it does. It controls the amount of pressure. It's the pressure decreaser. So it can't raise the pressure. All it can do is decrease the pressure. It's just a question of by how much, right? If it's a fixed orifice, whether it's a header crimp or a capillary tube or a piston, it's only doing it just with an orifice, right? And so it's a pressure drop across that orifice that's proportional to the pressure differential. It's really pressure in, pressure out, very simple. So that's what you're basically looking for, is where is the metering device, and if you don't find it anywhere else, it's obviously going to be there. But this is just sort of a, I mean, in my opinion, this is sort of a poor design, because this is not a valuable measurement in heat mode. I mean, maybe it could be if you had a chart to reference or something, but we don't. So it's not a valuable measurement. So you got to move suction side here, high side here. Pretty much every other system, you can just leave your high side on the liquid line and then connect the common suction. And the common suction is located a lot of different places. Like Train, because they're generally their reversing valves are in the in between the coil and the panel, which is a really nice place to put a reversing valve. You can actually just attach right above and below the reversing valve, so it becomes more obvious. It is kind of a nice. That's one thing that Train does that I do like. Go ahead, Eric.
I was going to say, if you're working on this equipment a lot, is there any kind of rule of thumb pressure drop across the evaporator so you can take a discharge measurement, take a liquid line temperature, and try to extrapolate subcooling?
Not that I'm aware of. I'm sure if you did those measurements enough, you probably could. Jim Bergman claims, if I remember correctly, 10 to 15 psi is a standard pressure drop across a condenser coil, a residential condenser coil. So that's the difference between your discharge, your typical discharge pressure, and your typical liquid pressure, but that's not going to hold true for your indoor coil. And again, when we're talking about heat pumps, the language becomes confusing because we can't just call the indoor coil an evaporator coil anymore. You know, it's the artist formerly known as the evaporator coil. Now it's the condenser. So that's why I tend to refer to them as the indoor coil and the outdoor coil, and they're a condenser or evaporator depending on whether or not you're in heating season or cooling season. All right? Cool. Any questions about that? Any comments? Anything we want to add? So connecting in the right spot, paying attention to where your metering device is. Obviously, I'm not going to read all the text here, but we're going to hit some kind of key points here. One of the most important things, we're going to go to kind of step 1 and step 2 here. Step 1 is if there's any frost, if you're running a system in heat mode and it's a heat pump and there's any frost in the outdoor coil, get the frost off before you take any measurements. Because frost, obviously, is going to impede your airflow and it's going to mess up your measurements. You can't compensate for that. Go ahead, Bert.
How do we get the frost off?
How would you get the frost off, Bert?
I would energize the reversing valve.
Okay. Run it and cool.
Yeah.
And get the frost off that way. Probably the easiest way. Yeah. Yep. So first do that, and then next check all the obvious things. Before you're going to do anything, especially before you're going to start messing with charge levels on a system, or you're going to condemn any parts, check everything that's obvious first. This is where, and I beat this dead horse a lot, talking about wide, narrow, wide diagnosis. So when you walk up to a system, it doesn't matter if it's a heat pump, straight cool, gas furnace, heat mode, cool mode, doesn't matter. When you walk up to a unit, first take a really broad view. Because what I see a lot of newer techs do is they'll go up to a unit, they'll be like, oh, the evaporator coil's dirty. Mrs. Jones, you need to clean the evaporator coil, right? And then they didn't notice that like the capacitor was failed and the compressor had blown up, blew a terminal and like all this other stuff. So you approve the evaporator coil cleaning, that gets done, and oh, by the way, you know, like that sort of thing happens a lot actually. And it's not wrong because you do want to pay attention to the fact that the coil needs cleaned. You do want to pay attention to the fact that the blower wheel is dirty, the filter, all that. But you got to do all of it first. You can't just do one, stop, and quote the customer. So that's why we start wide. We start by looking at everything, taking note of standard stuff, filter, evaporator condenser coil, blower wheel, so on and so forth. Anything else that you can visually notice about the equipment. Go through all that and then find the problem. So that's where narrow comes in. Start wide, go narrow, find the problem, find the thing that's keeping the equipment from working, quote the customer appropriately, always preparing them that you don't fully know until you do the testing once you get it fully operational. So just remind you, this is the battery of things that we're suggesting, bundle, whatever. This is the main problem. Once I get that all done, I'm gonna run test the equipment, check everything, and make sure there's no other additional problems. Makes sense? That kind of prevents a lot of heartache, especially with the impulse that we have to rush to the customer and say, I found the problem. It's simple, it's a capacitor, right? Or I found the problem, it's simple, it's a drain. That sort of language gets us into more trouble than anything else we do in the field. Because we want to get in, for whatever reason, especially as residential service technicians, we want to get in and out. I don't know why. Like we don't want to be with that one customer very long. We want to get to the next job. It's a really bad impulse. In heating season, it gets worse because we're not used to it as much. We don't have as much reps on it. We don't have as much experience with it. So you can make more mistakes. When charging in heat mode, read your manufacturer specs first. Because even within brands, there's going to be variation on heat pumps, depending on the compressor technology, depending on coil size. There's going to be a lot of factors that impact how you charge these things. We got some rules of thumb, but they're just rules of thumb. They're just there to kind of say, all right, I can tell that the system is basically working okay with no major, huge glaring issues, but it's not the best way. The best way is to follow the manufacturer's specifications. Now, Lennox is one that actually tells you to block off your condenser and do your tests in cool mode even when it's cold outside. So they tell you to do that. It's not my favorite way. I would probably prefer to use the field piece charging jacket. If you're going to do that, it's going to be a lot easier than trying to carry it's like one of those things like who carries a bunch of cardboard in their truck? You know, it's sort of a weird. Eric does for that purpose.
Mostly for refrigeration condensers, blocking them.
Blocking them off, yeah.
But it's the same concept.
Yeah.
You just find the right size box and fold it up and stick it in your truck somewhere.
Can't you just block off the condenser fan to raise the head pressure to charge it in cool mode the same way?
It cavitates, and so it isn't as reliable. It's hard to kind of get it dialed in, because in order to do it accurately, it's not just a matter of blocking it off, it's a matter of getting it blocked off appropriately so you actually get to your desired subcool level.
So what I was told is take the temperature coming off the fan, and you want it roughly 95 degrees coming out of the system to simulate a 95 degree temperature outside to charge in an appropriate cool mode setting.
I mean, that's not going to simulate a 95 degree day just because it's 95 degrees coming out. If it's 95 degrees coming out, you're simulating significantly less than a 95 degree day. Because that would mean on a 95 degree day, the air blowing out the top of your condenser is 95 degrees, and of course it's not. So, and that varies wildly. So that's what we call condenser delta T. And condenser delta T, if you've ever measured it, meaning the air temperature differential, it's highly variant. And the big reason that it is because manufacturers use the same condenser coil size and the same fans over a wide variety of tonnages. You'll notice this, like on a lot of systems, the 3-ton and the 4-ton box is the same size. So that condenser coil is the same size. So your delta T swings a lot depending on manufacturer, depending on coil size. There's just a lot of variables, and that makes it kind of challenging. Now, that isn't to say that it's not okay to do, but it's another rule of thumb and a battery of rule of thumbs, basically. The best way that I know how to do it, and it's not that expensive, is the Lennox, the field piece charging jacket. It's probably the best way. If you're going to do that practice, honestly, if I show up on a Lennox system, I'm not going to do it their way, but it's good to know their way. I'm going to go ahead and just run into heat mode and use my rules of thumb and make sure that it's in the ballpark and move on. If I'm going to do a significant repair, like a compressor replacement or something like that, then I'm going to weigh in the charge. I'm going to look at line length and I'm going to actually weigh in the charge appropriately. And then I'm going to do my kind of rule of thumb tests. So I don't love Lennox's way, but it makes sense. Like I understand why they're doing it. It's just it's highly variable and it's hard to pin down. What were you going to say? You look at
If you don't have cardboard, you can use a trash bag too. And you can just start creeping it around the condenser until you get the appropriate amount of.
Yeah, actually that's a good idea. Yeah. So this is an old school heating check chart that Carrier used to have. I inverted the colors just to make it easier to read. And so here, you're literally just looking at what is your dry bulb, wet bulb being the more accurate number here. What is the outdoor wet bulb temperature? What is the indoor dry bulb? You go across, what are your pressures supposed to be? And again, even that is it's kind of a rule of thumb. I mean, it's not going to be super exact, but the manufacturer put it out. So yeah, it always frustrates me when people use rule of thumbs on a system that has a chart like this. If it's got a chart like this, use the chart, right? It's a piece of cake. Now, one of the biggest questions is when do you use heat mode charging and when do you use cooling charging techniques? Does anybody know where the cutoff line is, temperature-wise? When do you charge? When do you check in heat mode? When do you check in cool mode? Does it say on here?
It usually says, I think 60, 65.
Yeah. 65 is typical. It's not always 65. 60 to 65 is typical. So when it gets below 65 degrees outside, that's when you're going to follow the heat mode test or low ambient check guidelines. Obviously, if you're at 65 degrees, you gotta probably just check it in both modes. And really, checking it in both modes when you're in the edge season is your best bet anyway. You know, if it's anywhere from 60 to 70 degrees outside, checking it and heating and cooling, a little bit of runtime is going to be your best bet. Next rule of thumb, the good old 100-degree over ambient discharge rule. So those of you who have been doing this a while, do you like that rule of thumb? Bert, Sam?
I hated it at first.
Okay.
I found it was more accurate when I actually let the system run a lot longer than I realized.
Yes. Very good point.
So
Very good point.
I never saw any consistency, and I didn't realize, 25, maybe longer, 25 minutes, maybe longer, it has to go.
Yeah, and that's true of any charging, anything like that. You can't run a system 5 minutes and set a charge. You can run it 5 minutes and know whether it's flat or whether it's significantly low, but you're not going to be able to set a charge in. It drives me crazy when I see people, it's like, oh, my subcool's 6, let's start adding some refrigerant, and the things run 5 minutes. It's like, no. Obviously, if your suction pressure on a 95-degree day outside is giving you 90 or 25 degrees suction saturation, well then at that point it's low, but not if it's just showing a little low subcool. You gotta let it run long enough before you start messing with it.
The reason I don't use it as much is because a lot of times you're showing up in the winter for us doing a maintenance, and you don't usually want to run the customer's heat 30 minutes. Around here it gets pretty hot in there. So
yeah, and that does make it tough for that purpose.
But
At
it
least,
does work if you're doing a diagnostic, you're trying to figure it out. It is a pretty decent range if you let it run long enough.
Yeah. So the rule is more like 100 to 110 degrees has been my experience. And the way this works is you run a system in heat mode, like Bert says, for a reasonable amount of time, 15, 20, 30 minutes. And then you measure your discharge line temperature at the outdoor unit, and it's generally going to be around 100 to 110 degrees hotter than the outdoor temperature. So if it's 55 degrees outside, it's going to be 155 to 165. Now, if it's significantly higher or lower than that, that's when it kind of gets weird because it's sort of a bell curve. Like, you can start to see weird measurements on both sides, like if it's really low or if it's really overcharged. But it's really more of an aid to just say, okay, if you're in that range, that's a pretty good indication that you've got at least close to sufficient charge. Any dispute of that? Okay.
Not really a heat pump guy.
That's right. Eric's not a heat pump guy. All right. So this is an example of me making this test with my old fluke clamp. And you're literally you don't even have to do this measurement. You don't even need gauges. It's just a measurement of your discharge line, the artist formerly known as your suction line, your vapor line, and comparing it to outdoor temperature. So if it's 58 degrees outside, that would be appropriate temperature.
And as it turns out, that is about what it was that day, or 60 degrees in that range. So that is an indication of a system that's at least close to proper operation.
I don't know. I zoned out for the last 30 minutes, but if you said this already, just let me know.
Okay.
But you have to inspect the system first. Like if you have clogged condenser coils, and
Yeah.
now your evaporator,
Right.
like you
Yeah.
can compare it to the outdoor temperature
Right.
because you don't even have a clean coil.
Did I mention that first, that you got to? Yeah,
Filters.
I did. Yeah.
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 Can we go
Weren't
back
you
to
sitting
where we
right?
were?
Weren't you sitting right here when that happened?
Yeah, and I gave input about it.
Did you? Oh, okay. But then you just forgot that it existed.
It just needs to be mentioned again. You
Oh.
can't just go off of the outdoor temperature.
Correct.
You have
Some
dirty
other-
coil
right.
or a filter inside that's really dirty.
Right.
Other things that are affecting the
Mhm.
system in an extreme way.
Absolutely. Bert, beautiful. All right, the suction pressure evap DTD rule of thumb. So back when we worked on R22 systems, there was just this weird coincidence that your suction pressure on a properly charged system would be about the same as your outdoor temperature. So I want to say this again, it's just a fluke. that if it was like 50 degrees outside, your suction pressure on an R22 system would be about 50. Yes, Bert?
I noticed that that didn't apply if you had a really clogged coil outside. Sometimes the digital inside.
You're Barney Fifing this thing up right now. Yeah, right. That's the reason why you're doing it, is to indicate whether or not you could have other problems. But to convert that to modern refrigerants, instead of using this weird pressure to temperature strange relationship, instead you do 20 to 25 degrees suction saturation below outdoor ambient. So you take your outdoor temperature, so say your outdoor temperature is 40 degrees, so it's a really cold day, then you're going to be somewhere between 15 and 20 degrees suction saturation, meaning your evaporator temperature. There's a lot of different names for these things, but the correlating temperature that goes along with your suction pressure is going to be 15 to 20 degrees Fahrenheit. Does that make sense, what I'm saying there? So, Joel, you walk up to a house and you're going to check in heat mode and it's cold outside and you're like, because this is practical, let's get nitty gritty here for newer techs. You walk up to a house and you're like, it's cold outside, I want to check this system. You hook up your suction gauge and you're like, holy moly, this thing is flat. It's really low, right? You got to remember that when the outdoor temperature drops, your suction pressure is going to drop, and it's going to drop proportionally with your outdoor temperature. So your evaporator temperature is going to drop along with your outdoor temperature. In the same way that your suction pressure drops when indoor temperature drops on cooling mode. So if you ever noticed, if you start a unit up and it's really hot inside the house, your suction pressure is really high, and then when it starts to cool down, it comes down, and that's typically a 35 degree DTD, design temperature difference. 35 degrees less than the indoor temperature is what you find in cooling. In heating, it's more 20 to 25 degrees. It's because one reason is because it's a much larger coil proportionally, so it's a very large evaporator coil. So that's actually a pretty good indication. And the nice thing about that rule is that rule is going to hold true no matter what happens with new refrigerants. It's not going to change too much because there's some limits to physics that cause that to be there. That rule is going to kind of remain. So if you go to a house, so let's make it practical, go to a house and it's 30 degrees outside and you hook up to it and you see that your suction saturation is 5 degrees. You're going to think, oh my gosh, this thing's going to freeze up. This is terrible. This is low. Yes, it will freeze up. And that's why you have defrost, because it's a heat pump. And so that's appropriate. But if you hook up to it, it's 30 degrees outside, and you hook up and your suction saturation is -10, then that's a problem, right? Or your suction saturation is 30 degrees outside, and your suction saturation is 20, then that's going to likely be a problem. So just gives you a nice rule of thumb. And this is actually, of the rules of thumb, this is probably my favorite one in heat mode, because it doesn't require as much runtime. It's not relying on like the thermal conductivity and the distance between the compressor and where you're measuring, because even with your discharge temperature over ambient, it really depends on where you put that clamp, because that temperature changes pretty quick depending on where you put the clamp. You put that clamp right near the compressor, it's going to be significantly higher temperature, which actually comes up when you're working on a heat pump package unit. You hook up right next to the compressor and it's like, whoa, my I don't know that you'll say, whoa, like that, but you might, you never know. Whoa, whoa, Nelly, this thing is hot, hotter than Hades. All right, so that's a good rule of thumb. Next one is head pressure, or CTOA. CTOA stands for what? Does anybody know what CTOA stands for? Condensing temperature over ambient, right? Now, where is your condenser in heat mode? Inside, right? So whereas condensing temperature over ambient and cooling mode is about the relationship between your condensing temperature and your outdoor temperature, in heating mode it's about the relationship between your condensing temperature, your high side gauge pressure correlated to a temperature, and your indoor temperature, okay? Now, opposite of where in heating mode your DTD is lower on the evap side, now it's going to be higher. So 30 to 40 degrees condensing temperature over ambient is going to be typical, but it's highly variable. And the reason it's highly variable is because that's very much tied to airflow indoors and coil size. So if you have an oversized evaporator coil inside, you're going to run a lower DTD, condensing temperature over ambient, or CTOA. So all that means is that you're going to run higher head pressure when you have a smaller coil with lower airflow, and you're going to run lower head pressure when you have a larger coil with higher airflow. And because systems aren't all the same, that's going to vary quite a bit in heat mode.
So when try to test it in heat mode, then if it has a variable speed motor, she test it at the highest speed setting.
You want to test it at the speed that it would normally operate at high stage. Like you don't want to trick it. Like you don't want to go in and tell it to run high speed when that's not what you're going to leave it at, obviously. But I'm actually a pretty big fan of running your heat pump airflows at high, higher speeds, and that's Carrier's traditional heat pump efficiency mode, because they have heat pump comfort and heat pump efficiency. That's what that is. At least they changed it. I'm speaking, and now I may be saying the wrong thing, but at least it used to be this way, where when you would put it on heat pump efficiency, it would run higher airflow in heat mode. So let's ask the question while we're on the topic. Why would people think it's more comfortable to run lower airflow in heat mode on a heat pump? Why would they think that? Anyone? Why would it be more comfortable to people to run lower airflow in heat mode on a heat pump? Air comes out warmer. When there's less airflow, the air comes out warmer. But what happens to the system when there's less airflow in heat mode? Inside. Compression ratio goes higher, head pressure increases. I said that opposite direction of what I wanted to. Head pressure increases, therefore your compression ratio is higher. So what does that mean? That means the system is not running as efficiently. It's not putting out as much capacity, and it's harder on the system. The compressor's running hotter. Compressors that are running with higher compression ratios run hotter. So I don't love it. Systems would run better with higher heat pump airflow, but the downside is, customer, that air don't feel hot. That's what that is. And that's exactly how they all talk too. That airflow ain't hot. Just like that. So if it were up to me in heat mode, I would run higher airflow, so bring your head pressure down. If you're running a system that has high head pressure, we'll just go ahead and jump to this since we're talking about it. You hook up to a system, your discharge pressure or your liquid pressure is really high. Don't jump to the thing's overcharged. That's everybody. I'll start dumping some charge out of this thing. Same thing with heat pump pool heaters. First thing people do, they see the high pressure. Somebody overcharged this thing. I mean, they may have, but in many cases, it's that you don't have proper airflow over your evaporator coil. On a pool heater, it's that you don't have proper water flow. So you're not moving enough water. So dirty air filters, dirty blower wheels, dirty evaporator coils, blocked returns, kinked ducts, returns that are collapsed, whatever, all those sorts of things are what cause high head pressure on heat pump systems in heat mode. Those are the most common things. And actually another very interesting thing that you see a lot of times is you'll go up to a system, because in Florida you'll have a cold night and then you'll have a hot day and a cold night and a hot day. So people will be shifting in between heat and cool all the time. You'll go to one of these older, Rheem used to have these resettable high pressure switches, these red buttons. You'll go out and the red button will be tripped. But now it's, a warm day, so they're running, you reset it, running cool mode, it's running just fine. No problem. What's the problem? I don't know what's going on. I guess we just have to keep mashing that red button. But they were notorious for bad airflow with certain models. It wasn't necessarily their fault. It was the way people were installing them. They weren't following the manual, but they were notorious with airflow problems. And so when you have poor airflow inside on a heat pump, that head pressure can go up quick. And on some models, it can go up really quick, depending on the size of the coil and some other things.
Those were also notorious for leaking on that switch.
Leaking on the
Push button.
I never saw that. Leaking refrigerant?
Never ever.
They would leak.
You've never seen that?
Nope.
I haven't either.
This guy's crazy.
I know, he's a lunatic.
Oh my god.
I thought he doesn't work on heat pumps.
What is that?
What's he talking
Put them
about?
on the straight cools too.
Oh, okay. They do?
They did.
Okay.
I
They
know
always
exactly
leaked
what
on
you're
the
talking
straight
about.
cools. I forgot
The
about
red
that.
button on the outside.
Yep. Yep, and sometimes they put a
Why would you want to
quig,
add heat to this?
and sometimes they put a quigulator on it. Isn't that what it's called, a quigulator?
Charge compensator.
Yeah, but what do they go?
Had different styles.
Quigulator, yeah. Yeah, we could talk about charge compensators. That's a fun conversation. But anyway, so we're talking about just some basic rules of thumb. So 30 to 40 degrees condensing temperature above the indoor dry bulb. So here's what that looks like, Joel. So you walk up to a unit, and it's in winter, and it's 65 degrees inside the house. That means that you would expect your condensing temperature, meaning, you look at your outside gauge, you look at what temperature that correlates to be somewhere between, I forgot what number I said, 95 and 105. That's what you would expect it to be based on that indoor temperature. If it's 125, 135, 145, look at airflow first. Start there. If it's
too high.
because that's too high.
That's
Right,
a really
that pressure's too high. Yeah. Another thing that's kind of interesting with heat pumps, and we'll just talk about this quickly, is that their capacity is highly variable, meaning that in air conditioners, we don't see a huge swing in how much capacity they produce, especially in a market like ours. So, the system, 3-ton unit isn't going to produce significantly different capacity. I mean, a little bit, but it's not going to be a huge swing from it being 75 degrees outside to it being 95 degrees outside. If you're in Phoenix, Arizona, and it's 130 or something crazy like that, or Death Valley, then yes, the capacity drops off a lot. But a heat pump, we expect it to run under a much wider range of conditions. So we expect it to heat somebody's house when it's 55 degrees outside, and we expect it to heat somebody's house when it's 0 outside. And we're talking Florida here, because it does get that cold sometimes, especially if you go north to villages, Ocala, that sort of thing. So that's a wide range. And the amount of heat that a heat pump produces when it's 55 degrees outside and the amount of heat that it produces when it's 0 outside is significantly different. Not just because it's more challenging to get BTUs out of that outdoor air. Just waiting for Bert. We're just going to wait. We're just going to wait. Sometimes you just have to wait. It's because when that outdoor temperature drops, what happens to your suction pressure? We already talked about this, so I want some of the younger guys. What happens to your suction pressure when outdoor temperature drops in heat mode on a heat pump? Drops, right? So when your suction pressure drops, but your indoor temperature stays the same, right? What happens to your condensing temperature? If the indoor temperature is staying the same or trying to hold the same, does your condensing temperature drop? It's not a trick question. A little bit it might, but it's not going to be a lot. And so what happens when your head pressure stays almost the same and your suction pressure drops? What do they call this differential between suction pressure and head pressure? Anybody know what that's called? Compression ratio. Compression ratio. The higher the compression ratio, the less refrigerant that compressor can move. And the easiest way to think of it, and we've talked about this in the past, is simply because when you drop suction pressure, what's happening to your gas? It's getting lighter. So meaning it's less dense. And when you have less dense gas and you've got this compressor pumping away, it has less to grab onto. It's like running a fan at altitude where the air is thinner and lighter. You're not going to move as much air because there's less air to move, and the same thing is true with the compressor. When suction gas gets less dense, the colder it gets outside, the less refrigerant it moves. So when you think about the magic of, just kind of segue to like modern inverter-driven compressors, because you'll see like these things keep their full capacity all the way down to 0 degrees or negative 20 degrees or whatever. You ever wondered how they do that?
Yeah.
How do they do it?
I've wondered it.
But you don't know?
No, I don't.
Okay, how they do it is that as that suction gas density decreases, they just start spinning the compressors faster. That's all. So they're not as efficient, but at least they can maintain their capacity. So in order to, as it gets colder and colder outside, as that gas gets lighter and lighter, and naturally that compressor is going to move less and less, you spin the compressor faster, you can keep the capacity up. Make sense? And that's why, when the green speed first came out, you had to put those giant mufflers on them, because when that compressor starts spinning up at these really high RPMs, you get this strange resonance that makes all kinds of crazy noises, because you're spinning the compressor faster than you've ever spun those compressors before. Now, obviously, they have to be designed for it, so it's not like they're not designed for it, but you get weird noises when things move at higher frequencies than normally they would. Make sense? Mm-hmm. So you learned something new, didn't you? Mm-hmm. Would you look at that? Would you look at it? Would you just look at it?
If you find on Copeland's app a compressor that's rated for air conditioning and refrigeration, you can see exactly how much capacity you're losing by dropping evaporator temperature. And I remember looking at one that was 20 tons of cooling for air conditioning. As a freezer, it was 4 tons.
Oh yeah, that's
dropping your evaporator 65 degrees, you went from 20 tons to 4 tons with the same compressor and electric input.
And you'll see that with low temp to medium temp too. I mean, you have a compressor that, if they can do both, when they get down to that lower edge of their operating envelope. Copeland talks about that all the time. Their operating envelope, meaning the conditions under which the compressor can operate. When you get down to the lower end of that, where you have higher compression ratio, and that's primarily due to lower suction pressure. Colder evaporator coil equals lower suction pressure. Simple concept, right? So if you're trying to keep ice cream cold, and you want to keep that ice cream negative 10 degrees, then you're going to have an evaporator coil that's lower than negative 10 degrees, right? So that means that if you got an evaporator coil that's negative 20 degrees, negative 25 degrees, whatever, That's very low suction pressure. And when you have very low suction pressure, you're still rejecting your heat to the outside, right? Even if so you have a grocery store, you're still rejecting heat outside, which means head pressure is still staying up here, but suction pressure is way down here. Big compression ratio, very little capacity. It's sort of a universal concept. And that's how we actually get more efficiency out of systems, meaning we spend less and we get more capacity is by dropping compression ratios. And the easiest way they always found to do that was big evaporator coils, lots of airflow, big condenser coils, lots of airflow. So you're just rejecting both sides. You're keeping your evaporator temperature up, you're keeping your condensing temperature down, better capacity. All was great until we realized they didn't dehumidify worth a crap when they're set up that way. So it's like a problem, but that's a Florida thing. All right, so checking without gauges. So I like to do heat pump tests without gauges where possible. Now, I just told you that my favorite test is just looking at suction saturation compared to outdoor temperature, and that does require gauges. But these are some things you can do to check it without gauges. Again, it's got to be frost-free. The outdoor temps need to be between 65 and 15 degrees Fahrenheit. Again, most of this stuff I just literally pulled out of my rear end. I just made up, kind of basing it on my experience and what manufacturers say. So don't take it too seriously. And once you've already inspected the whole system, you've looked at evaporator coils, you've looked at filters, you've done all that, like Bert was about to mention again. So we first check the discharge vapor line. It should be 100 and 110 degrees above the outdoor ambient temperature. Your suction line temperature should be 5 to 15 degrees cooler than the outdoor temperature. Now this is taking into account superheat and my rule of thumb. Liquid line should be 3 to 15 degrees warmer than the indoor temperature. And delta T indoors, because this is the one that a lot of people are like, what should my delta T be? What should the difference be between my return and supply air temperature inside? It's going to vary wildly. Like wildly, because not only are there design differences in equipment, but there's also these huge swings in ambient conditions that you could be operating in. So you're going to see a much higher delta T in cases where you've got an evaporator coil that is small with low airflow and when it's warmer outside. And then the opposite is true in the other way. So it's just not that valuable. If you really want to do a very thorough job, you can do delivered capacity. Delivered capacity is easily done. So you take a digital psychrometer and return, supply, hook up to measure quick, you'll get a pretty good indication of what capacity that system's producing, but that capacity is going to vary a lot too, depending on what the outdoor temperature is. So you got to kind of like take it with a grain of salt or reference a manufacturer chart in order to know for sure.
Imagine using a chart and measure quick together, like a manufacturer chart and measure quick together. Like imagine how good you could be as a technician.
Yeah, why are you saying that? This feels like a setup.
I'm just imagine.
Oh.
I tend to imagine.
I can only imagine. Yeah. Mercy me, that bad boy. You know what I'm saying? All right. So, any questions about any of that?
Do you need a hygrometer when you're doing that?
No, you don't. You don't. It's just that's what's going to connect to the app that's going to make it the easiest to do. But no, you wouldn't. You could use regular thermometers for that matter. Because you don't have a latent change across a condenser coil.
Right.
Because you're not not dropping water in heat mode.
Right.
The reason why you need psychrometers or hygrometers, whatever you want to call them, in cooling mode is because a lot of that heat is latent and that makes it tricky. So you have to measure change in relative humidity or change in total moisture content as well. You have to compensate for the latent capacity. So those are the ways that you check. Now, if you we'll just back up again, because if you're doing a new install on a new piece of equipment and it's 40 degrees outside, I would much rather you follow the manufacturer specs, weigh the charge in, and in our market, just go back for half an hour another day and just double check. That would be my preference. Probably still not going to happen, but that would be what I would suggest to most people. If it's if you're in a market like ours where you just don't have that long of a cold snap season or a winter, I don't know why I called it cold snap season. That was a really weird name for the winter. That's what we call it back in the woods. We don't call it winter. We call it cold snap season. And Jimmy cracked corn, but I don't care. Anyway, so that's not how that goes.
I have no idea.
I don't know. I'm really confused. I'm totally confused now. Anyway, if you have a fairly short winter in your market, then you can always just go back once it's warm outside and actually check it using subcool method or whatever. If you're in a market where your winter is longer than your summer, then whatever practices make sense in your market is what I would suggest. But anyway. All right, so right now we're in cooling mode. If this were a Lennox system and we were wanting to drive up our head pressure in order to test it in cooling mode with it being cool outside, we would use the charging jacket. So I want us to, it's not something we use a lot, but I want us to go ahead and just experiment with using that real quick. So I'm gonna give it to Joel to assemble. So if you read the instructions on it, it says only use on TXV systems. So this is for systems that you're going to be setting the subcooling in. This one's never been out of the bag before. So all we're going to do is hook these bad boys around the outside, like Trailer Park Girls. It's an Eminem reference, okay? Huh? That's how the song goes. Trailer Park Girls go around the outside, around the outside, around the outside, yeah.
The bottom is maybe one more.
Probably not, but I don't actually know that they're not, so it's not,
The top.
there's no impure thoughts for me.
Restricts airflow, and you can like adjust it.
Are you? Okay, all right. All right, so,
It's the worst jacket I've ever used.
huh?
It's the worst jacket I've ever used.
It doesn't keep you very warm. All right, so let's look at, this is Eric's. This is scary. Never grab another man's phone and just start flipping through it. That's something that I've learned a long time ago. Andrew Greaves about took Leilani's head off he was like, it's showing her something on his phone, and like, rather than just looking at it, she like grabbed it, and he's like, what are you doing? All right, so take a look at this. So right now we're at 99 degree saturation on the liquid side and 43 degree saturation on the suction side, which is fairly, to be expected. But if this was a cold day and we wanted to drive up our head pressure, and we can kind of keep this here.
Where do you want that?
You want it more loose so air can actually escape down the sides. So you're actually dumping hot air down the side.
Yep. And it says here what you would do. So in this one, you only use when the dry bulb temperature between 37 and 70 degrees. And you're supposed to keep it below 500 PSI for an R410A system. It says here, adjust the restriction of the charging jacket until the difference between the high side and the low side pressures is between 160 and 220 for R410A. So it gives you specific instructions on how you would use it, and then you're going to check your target subcool. Yeah, you see now we're at 100. We're at 117, 119. We're really getting there. So it's just more of a controlled way. Now again, we're running in cool mode, so this isn't really a heat mode test. This is just a way to check the charge in subcool with a TXV under certain load conditions, and it's actually fairly easy to do, so that you don't have to try to set a charge in heat mode. We're already at 450 PSI, so we can go ahead and, if you adjust it out, then you can get that head pressure back down again. All right. So now, we get the point. Let's go ahead and shut it off. And let's look at our defrost and inside our condenser a little bit. We'll talk a little bit about that.
Just leave this here.
No, we just take it off. Okay. That was all. Just demonstrating it. It's actually, I think it's a pretty good design, actually. It's easier than a lot of your options. All right, so first question is, why does a heat pump need defrost? But why will it frost up?
Yeah, why would it freeze?
But why?
Poor design?
Suction saturation drop.
Okay, so what do I call the evaporator coil? What's my kind of simplistic name for the evaporator coil? The heat absorber, right? And what direction does heat move? What direction does heat move?
Left to right.
It goes from higher temperature to lower temperature, right? So if I want to get heat out of the outside air and I want to get it into the evaporator coil, and the outside air is 30 degrees, what do I have to do to the evaporator coil in order to get heat to move into it?
Get it below 30.
I got to get it below 30 degrees, right? I have to get it below 30 degrees. And if the evaporator coil is below 30 degrees, because this is the evaporator coil in heat mode, right? What's going to happen to the surface of the evaporator coil eventually? It's going to freeze. And what are the factors that dictate how fast and how quickly, and how much ice is going to build up on that evaporator coil? Outdoor temperature. What else?
Outdoor humidity and airflow.
Outdoor humidity, airflow, runtime. Right? You got a system that's running a lot, it's going to be much more prone to freeze up than a system that's not running a lot. Stands to reason. What if it's raining? You know, what if there's like a light rain or something like that? And that could add to it, because now you actually have liquid water that's impacting the coil. If it's raining hard enough, it actually might prevent it from frosting, but depends on the temperature. So in Florida, we don't see a lot of sub 40 degree temperatures. It's not common, but it does happen. And when is it the coldest? In terms of nighttime. But what part of the night tends to be the coldest?
Nighttime.
Before the sun comes up.
Right before dawn. Right before the sun comes up. Yeah. Florence and the Machine, said it well. It's always darkest before the dawn and coldest. She didn't say that, but she meant it.
Wow.
She meant it. Yeah. She was. Yeah. Well, that was before she met the machine. Actually, that is the machine. The machine. Sorry, I'm a little slow right now. Yeah, it's the machine. Yeah. So anyway, and that's what tends to happen is, 4 a.m., 5 a.m., somebody hears a weird sound. They look outside, they notice their house is a little cold. They look outside, and what do they see? Does anyone know?
Steam.
They see smoke. So they see the white billowy smoke, and then what do they notice? So they say, oh my gosh, and what do? They run out, and then what do they notice?
They see it frozen.
Well, they might see ice, but they're gonna notice that the fan's not running, right? Usually what wakes them up in the first place is the weird noise though. And what does the weird noise sound like? Does anybody care to do a demonstration of what the weird noise sounds like when a unit goes into defrost? That's not all. Right? So literally, it is kind of funny. It's like manufacturers of heat pumps just set us up for people in the villages to go crazy and think that something horrible is happening. So it is. It's just a series of unfortunate events. So what do? They go out, and then they might just shut the unit off. They might shut the disconnect off. Well, then when they turn it back on, it's doing the same thing. It's still sitting there in defrost mode. And so that reaffirms their belief that it's a problem with the system. And then you go out and say there's nothing wrong. And as it turns out, they're an engineer and they know better. They have a friend who works at Disney World and told them that is not normal. And yeah, their nephew in Buffalo says you're full of baloney. So just being prepared and knowing that's how it works. In terms of sequence of operation, what happens is you have some method of the defrost board determining that it's icebound. Now, this is actually an interesting problem, though, because I want you to think like an engineer, okay? So forget what you know about defrost. Just forget what you know about it for a second. Because you knew nothing in the first place. Joel, forget what you know about defrost, all right? And imagine it's your job to design a method for this unit to know when it has ice on it, and then to defrost. And not just a little frost. It can't just be a little frost because a little frost happens quick. It's got to be like a decent amount of ice. So how are you going to design a control that goes into defrost when it needs to defrost based on the amount of ice that's on the coil? How would you do it?
Got it. We get like a scale underneath the condenser.
Right.
And we know the condenser weight.
Weight, right.
So the weight eventually is going to tip that point.
Right.
Running the defrost.
It's good. I like it. Any other ideas?
I'd be really lazy and just put a timer in and do it way too much so it never freezes.
Okay, that's one way. I like it. What else?
I'd hire someone at minimum wage to watch the condenser.
Let's go around with the flamethrower and just...
I feel like this is devolving.
Camera, watch it.
So one of the first ways that they used to do defrost is actually with a sail switch. So when the coil began to get icebound, there was a switch that would be, pulled up. It was a little sail, and it would be pulled up, and then, which by the way is my son's name, sail. Sorry. So then when it gets icebound, there's not enough airflow, and eventually the sail switch drops and defrosts. It's actually kind of a nice way of doing it. And another way to do it is with static pressure. You can actually use an accurate static pressure sensor, and the more icebound it gets, the more static pressure there is in the condenser. And I don't know why I'm telling you those two ways, because that's not the two ways that anyone does it anymore. Go ahead, Bert.
Why don't they do it like an ice machine, like a ice maker machine?
Okay, how's
would
that?
work too.
With like a sensor?
You actually have a bar that pushes out.
Yeah, so we just have we have a little thickness sensor. We can do it that way. Yeah. There's lots of ways that it could be done, but the way that a lot of people naturally think is, well, I'll just monitor the temperature, right? When that coil gets cold enough, I know it has ice on it, and then that means that it needs to defrost. But obviously that doesn't work, because in order for it to work, it's got to be below freezing, right? So I can't just monitor the temperature of the coil and say when it's cold, I defrost, because then it would defrost all the time. It would never heat. Does that make sense? Because it has to be a cold coil in order to get heat in it, the heat absorber, right? So they use a combination of two different strategies. So there's a method of demand defrost that actually looks at air temperature and then coil temperature, and over time it trends that and can tell when it begins to become icebound. So that's one method. That's what we'd call demand defrost. And then there is a time and temperature defrost, which is it uses a temperature sensor, and if that temperature sensor is below whatever the set temperature is on it, I think typically it's going to be in the 20s, and sufficient time has passed, then it's going to defrost. So it says, hey, enough time has passed, so I think I might need to defrost. Let's look at the sensor. Let's look at the thermostat. It's not really a sensor. It's just an open-closed thermostat. Is it open? Is it closed? If it's closed, okay, it's time to defrost. I'm going to defrost for a set period of time. Some of them are going to have a termination, so that once that opens up, then it's going to shut off, and some are just going to do it for a set amount of time. And again, this is sort of a common refrigeration strategy as well. But that's typically how it works. If you're in a market that it gets cold and you have a lot of defrost, and this is actually a pretty important thing to test. It's been something that I've been torn on, because a lot of people are like, you got to test defrost. Well, how often in our market does defrost really matter, like to someone's life? It's rare. Once every 5-6 years, there'll be a week or two, and then everybody freaks out like, how come you haven't been testing this on? It's like, it just doesn't matter. It doesn't make enough of a difference. But in markets where it is something that matters, and you do have pretty low temperatures, then testing defrost to make sure that they go into defrost does matter. But just keep in mind that the only way you're really going to test defrost is through a method that the manufacturer gives you to do it quickly, and even that's not perfect. Like, you're usually going to jumper out some pins and like, okay, it goes into cooling mode, so it defrosted, right? It's not like the full process. And for something like a carrier system, we actually have to jumper out the defrost thermostat in order to even get it to go into a defrost, because if it's warm outside, it's going to check the defrost thermostat, and it's going to be like, well, defrost thermostat's open, I don't need a defrost. So it's not even going to go into defrost. Make sense? Also, a really common thing in testing is they just have speed up pins. So there's an internal clock that checks every so often of runtime to see if it needs defrost. And that's what if you see those, 30, 60, 90, 120 second selectors, it's not second, minute. And then when you jumper those out, it just speeds it up. It's like 60 times or 100 times speeds it up. So rather than waiting, 90 minutes, it'll be 90 seconds before it checks for defrost again. It just speeds the clock up. Go ahead.
Has any of those strategies ever done just running the outdoor fan in the off cycle until the temperature actually gets below 32?
Yep.
running the outdoor fan in the
So
off
you-
cycle.
So
You disconnect the
Oh.
outdoor fan.
no, I'm saying if
And you let
Oh,
it
just a
breathe.
strategy. Okay, I see what you're saying.
cross strategy that runs the outdoor fan in the off cycle to keep the coil clear of ice. Has anyone
Oh.
ever tried that, or why not?
We're talking about something else.
I mean, it just depends on that might work, but usually on heat pumps, they're sized in such a way that when it's cold enough that you need defrost, they're running all the time. You know, that's kind of so that's not really going to be that helpful in those circumstances because it's diminishing. You know, because they diminish in output when you need the most. That's why people traditionally didn't like heat pumps, because when you need them to produce the most heat, that's when they produce the least heat. Right? They work great when it's not that cold outside, but the colder it got, they perform a lot better now because we can ramp the compressors up now. So with inverter technology, and that's why ductless systems produce really good capacity even at really low temperatures, because as it gets colder and colder, as that suction gas gets lighter and lighter, they just spin that compressor. And that's why you listen when you hear a ductless system running in heat mode. When it's really cold outside, they sound like they're whistling. I mean, they're just really, really buzzing because that compressor is really spinning in order to compensate for that lighter, less dense suction gas. Here you can see we've got our speed up, and that's what basically just speeds up the time in between checking. We've got a 30, 60, 90-minute pin here that we can select, but that's how you test on a carrier. On something like a train, you literally just jump between, you force a defrost, okay? But back to what happens during defrost, because I don't think I finished that story yet. What happens during defrost is shifts itself into cool. So once it says, I need to defrost, shifts itself into cool, shuts off the condenser fan, turns on the heat strips. And now the turning on the heat strips is actually one of the more interesting things that it does, because it turns them on by backfeeding them from the defrost board, right? This kind of an interesting thing with a heat pump is that you really almost have two thermostats. You have the thermostat inside, but then your defrost board kind of functions as a thermostat because it can also turn things on and off. And specifically, it can turn off the condenser fan and it can turn on your heat strips by backfeeding the white wire. And that's how that works.
And energize the reversing valve.
And energize the reversing valve, yeah. Energizing the reversing valve to throw it into cool mode. That's on your typical, carrier, train, Lennox, Rood Ream. This would be the opposite in some cases, so.
Would it energize why?
Would it energize why?
Let's say you drop the call inside right after you went into defrost.
No.
Dang it.
No, it doesn't. I don't know of any that actually energize why
I'm gonna have to
themselves.
test it at some point.
I don't think so.
Okay.
I don't know of any.
I'm gonna test it.
I just don't know of any. Let me tell you right now.
Well, it'd be easy to know, because does Y go straight to the contactor, or does it go to the board first?
Also,
It does go to the board first in a lot of cases, but that's for time delay. It is not energizing Y for the purpose of defrost. It's energizing orange, but if you lose your Y call, it's just gonna shut off. Right. I had an interesting thought that I was another thing that modern heat pumps also defrost faster. You know why they defrost faster?
No.
Because they have that ability to ramp the compressor up, so that way they can take that ability to produce hot gas and throw it into the outdoor coil quickly too. Now again, that comes at a cost. You don't get that for free. When they're ramping up a compressor, they're not running efficient. But guess what? They are running more efficient than. An inefficient heat pump is still more, and so I'm gonna say this again, because I rushed into it, so we're gonna back up, slow down. An inefficient heat pump is still much more efficient than what?
electric heat strip.
Electric heat strips, right. So in some cases, it's still more efficient than a gas furnace too. The thing that's interesting with gas furnaces is the price of fuel changes a lot. I mean, it's also true with electricity, but you have these two kind of moving scales. And so sometimes gas is more efficient or more economical, and sometimes it's not. Nowadays, heat pumps, because they've gotten more efficient, pretty much win out. Regardless of your climate, they pretty much win out as far as efficiency. They just have heartache associated with them, because in a gas furnace, let's say you have a 130,000 BTU gas furnace and it's negative 20 outside, and you fire on that gas furnace, guess how many BTUs it produces? 130,000 BTUs. Wow. If you have a heat pump, it may not produce its full rated capacity. And it starts off kind of behind the 8 ball as well. For those of you who have worked on pool heaters, you know the recovery time on a heat pump is significantly less. And it's just because it's less BTUs, right? You're limited, and it's actually an interesting thing in residences, something maybe we don't think about a lot. We're limited by the electrical service to a house, how big of units we can put on the house. So you have a regular residential house that maybe had a gas furnace before, they may have 100 or 150 amp service. You can only put so large of a air conditioning system on that. And even though it's more efficient, these systems require longer run times in order to do their job. And this is kind of an interesting, just a quick macro conversation about heat pumps. I love heat pumps, and I know a lot of people are like, go completely electric, get rid of all fossil fuel burning appliances. And I think, fossil fuels are kind of crappy in terms of like health issues in homes. You can carbon monoxide poisoning, risk of exploding your house. But the interesting thing is that if we all of a sudden put a heat pump in every house in America, it would completely shut down our electrical grid. Like, we're not even close to being able to handle complete electrification. So it's sort of a pipe dream. Like, we have to kind of slowly transition that way. In Florida, obviously, our grid is built for it, and so we're fine. But another interesting thing is that we think in Florida, it's like, our air conditioners run all the time. They run harder than anywhere. But actually, the temperature differential that's faced in the summer in Florida between what we want the inside of our house to be and what the outdoor temperature is actually not bad at all, compared to a place like Minnesota, where it may be 0 to -10 a lot, and they want it to be 65 degrees. If you do the math, that's 65 to 75 degrees differential between what the outdoor temperature is and where you're comfortable. Whereas in Florida, the maximum is maybe 30, right? It may be 100 degrees and we want it to be 70. That would be like the most extreme circumstance. So from a thermal, just a physics standpoint, what we're trying to do to stay comfortable is not nearly as complicated as what people in cold climates are. So that's where there's a much greater energy crisis in terms of that sort of thing.
But you won't necessarily see heat pumps though in those climates.
You do more and more. I mean, like even in places like Maine, they're taking off ductless technology, that sort of thing is really taking off. Boston, big time.
Would you still say that a heat pump is more efficient in those climates to a furnace, even though it has a longer runtime, versus a furnace with a very short runtime?
I mean, you have to do the math to see which is more efficient. But generally speaking, as a blanket statement, heat pumps tend to be more efficient nowadays. And efficient just means, all efficient means is BTUs to watts. How much money are you spending in watts in order to accomplish BTUs?
So you think on an energy bill, a heat pump would still be more efficient than a furnace, even in an extreme cold temperament?
It's going to generally be the case, yes. And again, it depends on the technology. If you're going with a single stage, unitary system like we install in Florida.
And a inverter.
Yep, an inverter heat pump, 90% furnace. In most markets, the inverter heat pump is going to be more efficient. Yeah. Now, it may not be able to do the job in a home that's built traditionally, which is where you couple that together with high performance building practices, much more better insulation, much tighter homes, that sort of thing. I mean, you can really decrease. I mean, an example is Bill Spone has I think his house is 2,400 square feet, something like that. Or maybe more than that. Do you know what it is, Max? Maybe more than that. But he cools and heats it with a 2-ton heat pump. That's the whole thing. He has heat strips installed, but he doesn't run them. And that's in Ohio, where it gets pretty cold. So, like, we wouldn't even want to try to do that here, let alone in a place that's significantly colder. So you can do it if you employ high performance building practices. But again, my reason for liking heat pumps, I don't care a ton about like the environmental, I care about the environment, but that sounded really bad. Like, that's not my primary motivation. I don't like gas because it is more dangerous. It's just intrinsically more dangerous for occupants and for indoor air quality, so.
What about the argument that a heat pump will experience more wear and tear because it's operating the outdoor unit in both heating season and cooling season?
I mean, it's true. Yeah, so I mean, in terms of lifetime, life expectancy of the unit, it's running twice as long, and depending on the design, it's probably running higher compression ratios. So it's a little rougher on it. The compressor's running a little hotter. It's a factor for sure.
Probably not good for it to sit for months and months at a time either, idle.
Yeah, true, and that's another side of it too. Yeah, I mean, a compressor just sitting still for a long period of time, or fan. Yeah, exactly. We see that with pool heaters, where you get compressors that lock when they've been off for a significant amount of time. It's much more likely. So.
Sorry, Nate Adams. I'm sticking with the furnace.
Do you like furnaces?
Yeah.
I actually like, so the thing I don't like about furnaces in Florida more than anything else is open combustion. So in Florida.
That's my favorite thing about them.
In Florida, we draw our combustion air through the front of a furnace, and that's a really dumb design. Like, if you go into a house, you have to have open combustion to an attic or outdoors or wherever, and that's a horrible setup. Sealed combustion makes furnaces a way better thing than when I don't care about high efficiency. In Florida, I wish we would do 80% furnaces because the efficiency doesn't matter, but do sealed combustion.
What about fuel oil itself?
Fuel oil
Furnaces.
I mean, I don't know anything about them. I mean, there's like a handful in Central Florida that have existed in the last 30 years. In markets that you're looking for inexpensive, but it's dirty. I mean, like they're a mess to maintain.
Purged, clean the combustion chamber, things like that.
Yeah. Yeah. So like the Northeast, they still use it. Midwest, common. I'm not an expert in that field at all. Still seems dirty. Again, when you're burning stuff, making explosions and fire in order to stay hot in your house, it just doesn't seem like the best design based on what we have nowadays. But again, recognizing that you can't just flip the switch. The grid won't support it. So, right now.
All the way back to defrost. You were saying so many good things, I didn't interrupt you.
Go ahead.
One of my bosses made this great video about checking in defrost, and it was on a Carrier system. And the way they recommend it is you just unplug the fan. So you're still actually testing the sensor.
Sure.
And you can do the time delay on the board.
Yeah, but it just still takes a long time.
It still takes longer.
Right.
But
it's a cost benefit analysis. Like, so you say you do 50 maintenances and you check 50 defrosts, and you have 1 out of 50 that actually has an issue. Is that worth the labor that it took to check those 50?
Not in Florida.
It just isn't in our market. And again, like, I don't like that because I love testing things and that's fun, right? I mean, it's another thing you can add to the process. So if you're looking to add something to the checklist just to do, fine. But in our market, I just don't think it's worth it.
But if you have a homeowner that's a hoverer, it's nice to show them how that defrost works. So.
And again, like a place like the Villages, it might be worth it because it's slightly colder. They are much more prone to like their heating matters more to them. Being a couple degrees uncomfortable means more. So in that market, it may make sense. Just, generally speaking, I don't think it does. But again, that's my opinion. That's kind of heresy to a lot of people. But anyway, it's like the whole process of testing, though, is always a tricky business. It's like when you start up a new unit, you start up a heat pump, brand new, you should really check every mode, right? So if it's a multi-stage equipment, you should check every stage. If it's 5 stages, you should go through all 5 stages, right? You should check it in heat mode. You should check emergency heat. You should check auxiliary heat. You should make sure the heat strips go on, they go off, which is fairly easy to do if you just go into the control and you just do the quick test, So let's say it's an Infinity or a Nest or whatever, and you just go in and you go into the installer setup and just run the modes, right? But is that the right way to test it? I mean, it's not realistic because you're not operating it in the way that it's actually as it would when the owner's using it. But is it better than nothing? Yeah, absolutely. And it is the way because you're always having to do this trade-off between time, effort, value, all those things. And so generally speaking, doing installer setup tests is the best way to test all your modes. And as an example, a lot of people will say, well, did you test the heat? Okay, if it's 90 degrees outside, you're not going to be testing a system in heat for anything more than a couple seconds. All you're going to be testing is to see if the reversing valve shifts, basically. I mean, you don't want to run that thing in heat for any amount of time. It's not good for it to run that way. But for example, doing your fall PMs, and we're going to talk about PMs as a separate class, but doing your fall PMs, you do need to be burning off your heat strips. You do need to be checking that. You don't want that customer to experience that smell, that odor of that system going on for the first time without you being there. It's much better to say, oh, what's that smell? Did someone catch on fire? Yeah, I'm just testing the heat strips. I'm just running it in heat for the first time. Than to have that happen when you're not there. So for those of you who maybe aren't doing that right now, as you go into fall PMs, you do need to run heat and test it. Do you have something you'd like to share with the entire class?
I'm sorry. I'm so sorry, Brian. Technician with bad breath was trying to read the error codes.
Just melt, yeah. Funny, hilarious. All right, that's all for today.
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing, You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.